Nate, for this very kind introduction. I actually got to Penn State in 2006, so I'm older than you thought. Anyway, as Nate said, the apples doesn't fall too far from the tree. So I'm going to be talking about 2D physics, but 2D physics done in graphene. And today I want to show you actually how we manipulate the Valley degrees of freedom in a material called bilayer graphene, especially using its topological properties to make electronics. So that's sort of the title. You will see what I mean by then. Tomorrow I have a seminar and we'll talk more about 2D physics in a magnetic field. So I have been here about maybe 7 to 8 years ago, so it's good to see the old faces and new faces again. I had a very enjoyable discussions with various people throughout the day, and I'm glad the parrot at Mission Inn is still there. So I don't know if it's the same parrot, but it's still got parrots there. To start, I want to give you pose a more general question, which is how do we transport charges in a wire resistance-free? Right? Okay. So this question is important because of a couple reasons. So we have computers with millions and millions of transistors on the chip. In order to operate them, we have layers and layers of copper interconnects, up to 11 layers in our microprocessors. And these interconnects consumes more than 50% of the power of the microprocessor. So reducing the resistance of your wires is a very important question. Some of you may know that we are in the middle of a quantum leap era where quantum computers may become reality in our lifetime. And this is a picture of a quantum 4-qubit chip made by IBM a few years ago now. And you can already see the amount of wiring that has to go in order to operate those 4 qubits. Now imagine if you need to scale this up to a quantum computer with many qubits. Right? So here it's not only a matter of energy consumption, resistance brings in also decoherence. So it's very important that we can transfer the quantum information coherently without losing them. Right? So how do we do that? So, as I alluded to, so if you're working with a superconductor, then superconductivity allows you to do that. Okay. So how does a superconductor transport charge resistance-free? So there are a couple of things happening in a superconductor. The very important thing here is that there is a gap opening at the Fermi level, where your electrons pair up to form bosons, and these bosons condense to energy below this gap over here. Okay? And these bosons move in locked steps, so phase coherent fashion. So if you imagine this is not the worst traffic jam ever, but rather a lot of bosons moving in locked step, all with the same velocity, then this would be a perfectly flowing traffic. Right? Okay. So this phase coherence is important, but also there are no states near the Fermi level where the paired up electrons can scatter into. So the chance of scatter out of this cohort is exponentially small as you increase the size of the gap. So opening the gap is really important for that. So that's how superconductivity do it. If you want to reduce resistance, reduce dimension would help. If you think about, again, traffic, okay, so if your electrons are billiard balls moving in 2 dimensions, you have a lot more chance of colliding with other electrons also moving in 2 dimensions, because you can collide in many different directions. Right? So more easily to be in a jammed position. Whereas if you have highways, electrons moving in 1 dimension, there's much smaller chance of doing that. So reduce the dimension also helps. And we have materials that where electron moves in 1D, nanoribbons, nanowires, nanotubes, and so on and so forth. Okay? Okay. So in fact, we can do a little better than this, because even if you have a one-dimensional surface, you can still have head-on collisions between two cars, right? So cars or electrons moving in opposite directions have a chance of scatter into each other. Right? Okay. Whereas if you have a divided highway, this chance is a lot smaller. Right? So here we're physically separating cars. Cars moving in this direction are on the right side. Cars moving in this direction are on the left side. Right? Much smaller chance of colliding and backscatter. Right? Okay. So if you have wires where electrons moving in opposite directions are physically separated from each other, that we call chiral edge states. And chiral edge states occur in a phenomena called the quantum Hall effect. They are the edge states of the quantum Hall effect sample. Okay. So quantum Hall effect started from classical Hall effect. You apply a magnetic field. Electrons feel the Lorentz force, and they go to the side of the sample. Positive charges go to one side, negative charge go to the other side. That sets up a Hall voltage. Okay? So that's the classical Hall effect. Now, if you start increasing the magnitude of the magnetic field, some of these guys will start forming a complete cyclotron orbit in the interior of the sample, like so. So you can see that they no longer transport a current because they're just circling on spot. Okay? Whereas the electrons at the edge can skip around. Okay? So collectively, this looks like a current going that way. This looks like a current going that way. So you already begin to see that in the quantum Hall effect, the bulk of the sample is an insulator, and the current is being carried by electrons running along the edge of the sample. Well, this picture is not quite correct. It's a classical picture. We have a quantum mechanical understanding of the quantum Hall effect as being the bulk opens up what's called Landau levels with a gap, delta. And this potential sort of rises up as the sample stops and there's a vacuum outside. And when you put your Fermi level here, the bulk is inside a gap, whereas the Fermi level cuts through these 2 points. Okay? This is actually both space and also momentum. So I have 2 wires at the edge of the sample with opposite group velocity d, dk, one pointing one way, the other one pointing the other way. Okay? And these are the edge states that I draw over here, these 2 sides. Okay? So as long as they're physically separated from each other far enough that there are no orbits that can connect them, you cannot scatter an electron from this edge to the other edge. Therefore, you will not incur resistance. And that's how edge states in a quantum Hall effect can transport charge without dissipation. Right? So in the way that I'm drawing over here, this edge state acquires a potential that is the same as the source, and this one acquires a potential same as the drain. In order to push an actual current in this direction, this guy must be a little higher than the other guy. So there's a voltage offset along the 2 terminals of your sample. And if you work out the mass, that corresponds to a conductance in the unit of E squared over H, if you actually measure. So when you hear a quantum wire is ballistic, it does not mean it has 0 resistance. It means you have quantized conductance there. And here I have 1 pair of counter-propagating edge states, and the 2-terminal conductance is 1 E squared over H. You can figure this out. So the chiral edge states of quantum Hall is the most robust wires of all. In fact, this robustness is up to, I don't know how many digits here, about 10 to the 9 also. And that gives a good measure of this fundamental constant combination, H over E squared. That is a resistance of about 25.8 kiloohms. This is also known as the von Klitzing constant. It's your resistor standard. In fact, it's so precise you can use a Watt balance to measure the gravitational force and therefore redefine the mass based on the electrostatic force over here. And that's being done to replace that platinum sphere that you all heard of in somewhere in Paris. Okay? Okay. So, but in order to achieve this quantum Hall effect, I have to apply a magnetic field. I have to break time reversal symmetry. You can see that I have a current going, circling clockwise, right? Okay. So can you do this without a magnetic field? Okay. So can you introduce new rules that could prevent this backscattering without using the physical separation of these states? So I want to sort of make an analogy. It's sort of like designing a highway system where you say cars traveling this way are all blue, and cars traveling this way all need to be red. And if you want to switch over, you have to go through a body shop and change your color. It's very artificial. Okay? But here I mean by color, so it's some sort of a quantum degree of freedom that you attach to the direction of propagation for the electron. If you could lock it to the propagation of that electron, and if you could reduce the number of body shops to 0, then the electrons have no way of backscatter, right? Okay. So this color over here could be electron spin, and when it's electron spin, we have spin momentum locked quantum wires. Okay? So this kind of system actually happens. And you can see that it doesn't break time reversal symmetry. Okay? Okay. Has both wires going this way versus and wires going that way. Okay? So this kind of wires occur in a phenomenon called the quantum spin Hall effect, okay? Or a two-dimensional topological insulator. So the way it works is that if you have a material where with some sort of interaction, and in this case, a spin-orbit coupling, that you somehow mix the piece of the conduction band, what was originally the conduction band, this color here into the valence band, and vice versa, you see it looks like I have some sort of an inversion of that band in that particular of the place of the momentum space. Or it looks like somehow I twisted a knot into the band structure. Okay? Okay. So if you have a material like this, a vacuum as we know it is a trivial insulator with bands that look like that. Right? Okay, you ask, how do you actually patch this up at the sample boundary over here? How do you get an electron in adiabatically from the vacuum into the material? And then the electron in the conduction band needs to go from here to here, right? Because it needs to find wave functions of similar symmetry there. And you realize that it could not do that unless this gap closes on the sample boundary, where this guy could smoothly go point through this point into here, and this one could smoothly go through this point into there. Okay? Okay. So a topological insulator has a surface state. A two-dimensional topological insulator, the surface is the one-dimensional boundary. Okay? So at the boundary of a two-dimensional topological insulator with vacuum, we have wires that are transmitting zero gap, zero mass states. So these are the spin momentum locked wires that I mentioned before. And you can see that the way that I'm drawing over here, if I look at spin up, it forms a loop. If I look at spin down, it forms the opposite loop. Right? So I didn't break time reversal symmetry. Okay? There is a way of counting the number of wires that you will get. Right? And that's in terms of a topological charge called a Chern number. You look at how much the Chern number changes as you go from a trivial insulator vacuum, which has a Chern number 0, to a non-trivial band structure, which has a finite Chern number. Chern number changes by 1 for one spin species. You get one set of channels. It's -1 for the opposite spin species. You get the counter-propagating states. Okay? So here I have two sets of counter-propagating wires at the boundary of the sample. And if I put a contact here, I put a contact there, each pair gives me 1 e² over h. I should expect 2 e² over h in my conductance. Okay. So they carry opposite spin indices. We call them spin helical. These are helical. It's a helical one-dimensional wire system. Right? Okay. So that's the quantum spin Hall effect. So quantum spin Hall effect was first discovered about 10 years ago by Mollenkamp's group in a material that gives you this inverted band structure through spin orbit coupling. Okay. And since then, there had been a lot more examples of this in different materials: graphene, bilayer system made of indium arsenide, gallium antimonide, and quite recently, 1T prime tungsten ditelluride. Right? I had a very nice conversation with Yung Tao earlier, who imaged these wires at the edge of the sample. But I want to point out some of the problems of this system. Right? So as you can see, the quantization of the conductance is really not that good. Right? This is a semi-log plot. This is not really a flat line, right? It has all this stuff. It's close to 2 e² over h, but not quite good. And in addition, the temperature that it survives is quite low. You need to go to dilution temperature to measure that. Right? This system over here, we expect 1 e² over h. We're getting a conductance below that. Right? Mean free path here is maybe about 100 nanometers. Okay? So there's something that scatters an electron from sort of in this counter-propagating system that flips the spin. Right? You have to flip a spin in order to do that. Right? So exactly what is doing that is an ongoing question. But there are some clues that we can already learn from the existing investigations. Right? And we know that in order to make these states robust, you want to open a large band gap. And these systems have a gap that's given by, let's say, the spin orbit coupling. So they're generally small, on the order of 10 millieV. Right? Remember what I said about the superconductivity gap. If you could move all the other states that the electrons can scatter into far away from your surface, you do much better in preserving the robustness of your system. Okay? So a bigger gap would help. And also higher quality samples where there are no states inside the gap that could mix with the quantum wires you want to protect is also something we would like to have. Right? So this is 10-year-old. It hasn't got much better than that, even today. So I want to show you something different. I want to show you a new color that we can give the electrons. We talked about spin being the degree of freedom. Today, I want to talk about how we create these valley momentum locked wires that would give you also ballistic transport in these 1D systems. So I will explain in a moment what valley is and so on and so forth. So I want to talk about two things. First, I want to show you how we created this system. These counter-propagating wires that carry different valley indices and their properties. And then I want to show you actually if you have more than one channel. In this case, we have a cross. So we can ask the question, if I send in current through one terminal, how does it go? Right? Which outlet should it go? And can we control the transmission with preferably electrical signals? It turned out that we can. And I want to show you two operations. The first one is that of a valve. And the second one is that of a tunable beam splitter. Okay. So we got to take some hints from the quantum spin Hall effect. It is there because we had a non-trivial topology in the material. Okay? So, and that involved inverting part of the band structure of the topological insulator. Okay? So I have a recipe here. Okay, how do we do that? We need to invert the band somehow. So let's start from a material with zero gap or a very small gap. If you start with something that has a 2 eV band gap, your interactions is not that strong. You can't invert that gap easily. And that's why topological insulators are narrow gap semiconductors. You don't find them in something like moly disulfide. Right? Okay. So I want to find a small gap material, zero gap material, and I want to add an interaction that opens a gap. I want to find a way of inverting that gap, and I want to put the positive gap and negative gap together as you saw before in the TI, and then I'm going to look for these counterpropagating states at the boundary between the positive and negatively gapped area. Okay, so that's our recipe. And the material we work with is graphene, more precisely bilayer graphene. So you probably have seen this, I don't know, 100 times now. By now, everyone recognizes the lattice structure of graphene, and the honeycomb lattice structure, the two sublattices, the hexagonal Brilliant zone. The thing I want to emphasize over here is that, in fact, there are two types of pockets in the Brilliant zone here, the K and K prime. And if you look at the bands of graphene, they're formed by the bonding and the anti-bonding orbitals, pi and pi star. Right? So this is pi star, and this is pi. And if you look at how these states thread through the black and the white points over here, you realize that they're different, right? If I'm sitting over here, I look to my left, I see a red band. If I'm standing here, I look to my left, I see a blue band. So if I reduce my band structure to the low energy structure near these points, these 2 points have different physics, different Hamiltonians. So indeed they do, and that's how it looks for these linearly dispersed bands here for these two different valleys. So the dispersion is linear, so I have two cones over here at those points over here. And the wave function equally occupies the A and B sublattice. Why should it not? They are equivalent. There is a symmetry between the two sublattices. And if you look at the way the wave function is constructed, indeed, it looks like a spinner, right? So spin up is one sublattice, spin down is the other sublattice. And I have 50% on one and 50% on the other with a phase angle. And that phase angle is related to the direction the momentum is pointing. So it winds around as you go around the Fermi surface. That's what's called the Barry phase. Okay. So graphene has no band gap because of this inversion symmetry between the A and B sublattice. To break that, in order to create a band gap, I have to make A and B different. So if you're a theorist, you can just add this by hand in your Hamiltonian. You add a potential to one sublattice, the black one. You add another one. You add let's say plus and minus delta over 2 to the other sublattice. Now if you're an electron, you prefer to sit on the site with lower energy. That would be the valence band. And your conduction band would be made up of the other types of balls, okay? And they're separated by a gap that is delta, right? Okay. So in order to invert that, okay, I can play a trick here. I can create a boundary where I have A sublattice black, black, and you see across this boundary, now this one becomes an open, okay? So plus, plus, now this one is minus, okay? Okay. So by doing that, I have inverted the band gap of my system. Okay? To the argument that I gave you before, at this, exactly at this domain wall, I would expect the gap to vanish, giving me these gapless modes, these wires that are counterpropagating along the domain wall. So if you're experimental, you realize, this looks like boron nitride, right? So we sort of want a twin boundary in boron nitride. You can't find a twin boundary in boron nitride. It's not energetically stable. Right? So how do you do this? So it's hard in graphene, actually, to do this. Right? So to give the two sublattices different potentials. But maybe we can find a way out by, whoa, what happened here? Well, actually, I wanted, before that, so I just wanted to briefly say that this is not something that's terribly new. Ignore this thing over here. I don't know what happened. This should be a band structure calculation. And it didn't copy well, I guess, when we shuffled it. But there's a polymer chain called a polyacetylene, right, where this alternation of single and double bonds open the band gap. And if you watch this single, double, single, single, double, single, double, can you see? You see there is a sort of a phase slip across this point over here. Okay? And that corresponds to a positive gap, a negative gap situation, and what's known as a kink in the polymer in the polymer field. Okay? If you have a network of these polyacetylene, these guys are the ones that carry the conduction through the network, okay? Through the gapless modes that I just mentioned. Right? This doesn't help us in making it in graphene, though, so I still had to think of something else. And that something else is to add another layer to it. So bilayer graphene stacked together in this fashion, AB stacked. Okay. That's how they look when we take them out of HOPG graphite and put it on an SiO2. A lot of people here work on two-dimensional materials. If I look at the side view of this stacking over here, these two guys interact strongly because they're stacked on top of each other, and they form these dashed bands that are away from the Fermi level. But B1 and A2, these two guys, are the ones that are responsible for the low energy bands. So this, the conduction and the valence band. And notice that there is also an inversion symmetry between them, just like the AB sublattice of graphene. So because of that, bilayer graphene has zero band gap also. Okay. But to break that symmetry, I can now apply an electric field perpendicularly through the sheet over here, and therefore giving them different electrostatic potentials. Now I have opened a gap in the spectrum of bilayer graphene, okay, over here. Okay. So in fact, this gap scales almost linearly with the applied electric field, the displacement field, and could go all the way up to about 250 millieV. 250 millieV, that is a pretty big gap. If you could put your wires inside that gap, right? So that's something that we hope to do. Yeah. So we measured this with transport, earlier samples on SiO2, cleaner samples sandwiched in between BN. That's these dots over there. Correct. Correct, and that's because of the cleanness of the sample, right? We can talk more, yeah. So these are measurements in BN sandwiched bilayer graphene. Okay. Moreover, you just flip the electric field, and then you would flip the sign of the gap, right? So that part is easily done now, because my gap is created within the electric field. Okay. So came a prediction about 10 years ago by Martin et al. Collaborators, and says if you could make a structure where you put 4 gates, 2 pairs of split gates, above and below the bilayer graphene sheets over here, and you apply an electric field pointing up in one on the left, putting the Fermi level at the charge neutrality point inside the gap, and then you do the opposite on this side over there. I create a band crossing that looks like so, gap, gap, gapless mode over there, and I should have counter-propagating edge states, right? So we call them kink states because they occur in the middle of the sample, kind of like the polymer. And that's a realistic calculation of what their wave functions look like. They look like counter-propagating wires living inside the junction that we created, right? K and K prime. So theory also says that you ought to have 4 pairs of them. Okay? And that 4 comes from counting that topological invariant, the Chern number that I talked about earlier. Okay. So This is for the theorists in the audience that the Valley churn number is not a good topological invariant, but the change of it across the junction is a good topological invariant. And my positive gap side has plus minus 1 for the two valleys, and my negative gap side has these two flipped. Remember, the physics is contrasting in K and K prime. A lot of them are in these hexagonal materials. Right? So I have a churn number change of plus 2 and minus 2 for these two valleys. And that should give me two pairs of counterpropagating states. But if you add now spin onto this, because we haven't talked about spin at all, right? So that multiplies by another 2. So we have totally 4 more modes going up in one valley and 4 modes going down in the other valley. That gives me a conductance of 4e squared over h if there's no backscattering between the counterpropagating modes. Okay. So that's what we will be looking for experimentally, this 4e squared over h in conductance. Okay. Realistically, we can't make an abruptly sharp junction. We are patterning this lithographically with a width of typically maybe about 60, 70 nanometers. Okay. So as a junction has a waist, it has a region where there could be states that live just inside the junction. Think of it as a narrow ribbon. Okay. They're quantum confined, so they don't go down to 0 energy, but they go down to some energy, and those are the blue states that are marked over there. Okay. So I have a bulk gap of delta, but my wires, my kink states, live inside a reduced gap of delta prime, which is smaller than the delta. Okay. But you can see that these red dispersions are the states living inside K. It has group velocity going one way, and then the states in K prime has dispersion, has group velocity going in the other way. Right? So that's the counterpropagating aspect. This is an artifact of calculation, so just ignore that. In order to backscatter, you need to take an electron from K to K prime. And K prime are separated by roughly 1 over the lattice constant. So you need a short-ranged impurity, atomic defect, to do that. There is this beautiful measurement by Elie Zeldov's group not long ago, using a scanning squid to actually measure individual phonon emissions locally. The phonons mediate inelastic scatterings that probes the number of atomic defects you have in the system. Okay? And graphene has 0 in the bulk. All that scattering occur around on the edge of the sample. So we have no atomic defect in our system. There's good hope that we would be able to preserve the ballisticity of the system. Right? So that's what we set out to do. Right? So this is a device that we're going to make. We're going to make a pair of, 2 pairs of split gates. The bottom are graphite, the top are gold. We're going to have a junction in the middle over here, put electric fields in opposite directions, put the Fermi level inside the gap so that this does not conduct. This does not conduct, but in the middle of these 2 insulators, we expect these counterpropagating states that we're going to measure from here to there. In addition to that, we also have a gate underneath, which we use to tune the Fermi level of the junction so that we can scan through this gapped regime. Okay. So since I came from the gallium arsenide field, so I just wanted to pause a moment and marvel about sort of how remarkable graphene materials are. Right? You see, we used to get samples from Loring Pfeiffer, which would look like this. Right? So in order to grow these high-quality 2-dimensional electron gas, we would pile up substrate. We have superlattice to trap impurities, barrier, doping, quantum well, barrier, doping, quantum well, barrier, and so on and so forth, right? This all happens in a MBE chamber with a very low pressure, right? You have UHV environment, right? Okay. So, and because the 2-DAG happens so deeply buried underneath the surface, which is what you need in order to get these high mobilities, devices that are made out of these materials typically have length scale on the order of a micron. You cannot make anything smaller because the confining potential is very soft because you're going really deep with your gate. Okay? Okay. And even samples that look like this, really giant centimeter-sized samples, work very well. Okay? Okay. So when you work in graphene, you don't need a collaborator like Lauren Pfeiffer, who has a MBE chamber to grow you. You just get a piece of HOPG graphite and start exfoliating, and your lattice is perfect. There's no defect whatsoever. So this really makes a level play field. And what we do in our lab, and many people do here as well, is using a technique pioneered by groups at Columbia, Philip Kim and Jim Hong, to stack graphene and insulator, this hexagonal boron nitride I mentioned to you, and use this as a protecting layer and a dielectric layer to gate our graphene samples. So we would put on a layer of graphite, let's say 3 nanometer thick. We would etch it into a split gate. We put on a layer of hexagonal boron nitride, say 20 nanometers. We put on a layer of bilayer graphene. We use E-beam to shape it into a hole bar. We put on another layer of HBN. We pattern the electrodes to our hole bar. And then in the end, we pattern the top split gate. Right? That stacking is happening in air on something that looks like this, right? Ambient conditions. Right? So this involves quite a bit of lithography steps we clean in between. In the end of the day, if you're successful, you end up with something that looks like this. That's a SEM image of a device. These black squares are the graphite backgate. This purple stuff is the bilayer graphene. This thing is the top BN. That's our top gates, those two goals. You can see that they're lined up with the bottom one over there. We're going to send current through these two and measure voltage with those two so that we measure transport along the junction. Okay. Okay. And we're going to use the silicon that's down there you don't see to control the Fermi level of the system. Okay. Okay. Yep.
The segments like outside of the gate region, these are semi-metal and these are ungapped bilayer graphene.
So the
like what you're labeling with I and D, are these gated?
So this is heavily doped. This is all heavily doped because they're only sitting on the back gate. The top gate is only here and there, so these are good leads to the graphene. Right. Right. We're using graphene leads to contact the channel, correct. Okay. Okay. So and then we got more ambitious because I need more than one channel to do the controlling. So we made a cross device, a 4-way junction over here, which involves 4 pairs of split gates, so 8. And then the 9th one that controls the Fermi level. So we're going to gap here, 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 here. And we expect these wires, this magenta cross that I drew, only living inside the area corresponding to the dual-gated regions. And we can measure, we can send in current from any of these terminals through this heavily doped area and then measure in any other terminals. We can also dope the bottom to just probe this one, rotate it around, studying all 4 wires, and then ask if I send a current in from one of these, which way does it go? Okay, so that's the splitting that I'll show you. Okay. So I'd be happy to explain more if anyone wants to know how these things are made and so on and so forth. But now I just want to show you some pictures, because this took my students a few years to figure out how to do all of that. Lithography and also keeping the sample quality high. Right? Sometimes it actually started out looking like this before it looked like that. Right? So if you're fighting lithographic problems, just know that there is a way forward, and I'll be happy to explain. Okay? What is critical in our device is to line up the top split and bottom split, right? Because we're only having 70 nanometer channel, and if you do an E-beam, you know that it's not easy to do that if you take the sample in and out and do things in between, right? So Jun figured out a way of doing that. In fact, these days we can do the alignment between different writings to better than 10 in both X and Y directions to make this cross structure. We can also carefully control sort of the lift-off and dimensions and so on and so forth. again, if anyone is interested, I'm happy to talk more about how we do these things. Okay.
The 70 nanometers, is that kind of the smallest you can get? Or is it
So when you do a liftoff process, when you go below 50, the failure rate starts to go up. I show you a failure of the liftoff, which looks like that and looks like that. So the smaller you make it, the more challenging it is. You can do better with etching. So we're moving into, huh?
what happens when you open it up?
Oh, okay, good. So I'm going there. So remember this band structure that I showed you, right? So if you make this real wide, what happens is now you have a wide nanoribbon. And states living inside that wide ribbon now drop lower in energy. So effectively, now your quantum wires living inside a smaller gap. And I want to make that gap as large as possible, right? So that's why you want to go narrow as far as lithography allows. Okay. So this is the geometry minus plus opposite gap that we have in order to create these kink states. I have a control configuration where I point the gap in both directions, in which case I just have the fringe field sort of connecting them, and there is now a gap inside. There's no states inside the gap. So by doing that, I can in situ, as we sweep the Fermi level, in this state, I expect high conductance inside the gap. In this state, should be insulating, right? So that's my reference to show that if I had anything inside the gap, it is because of the states, not because of impurities inside the gap, right? Okay. So that's indeed what we saw in our first experiment when we compared the resistance or conductance of the system in the directions, in the quadrants where I have this inverted structure. I see the resistance is very low, whereas in these two quadrants where I don't have an inverted band structure, the resistance is very high. This tells me that my kink states are indeed inside the band gap. Okay. But in our first run, if you have good eyes, you will see that these are not 6 kilo ohms. 6.5 is what I expect for h/4e squared, right? And these are larger than that. And it's only through improving the sample quality, making the interface cleaner and cleaner, that we are approaching that value in our second generation of devices, right? These crosses that I've shown you. So let me show you some of that data. So this is the configuration, again, where I have an inverted band structure, and I have these states, K and K prime, counterpropagating inside the channel. And you can see that in this regime, gapped regime, we get about 7 kilo ohms of resistance, and it's a plateau in this regime. Okay. If I do the control experiment plus, I have about 8 mega ohms, right? So no states inside. So why do I have 8 mega ohm? Why isn't it infinity? Okay. The reason for that is the fact that there's some conduction leaking through the gapped area. Okay. So like I've drawn over here. Okay. And this conduction, it's hopping through states inside the gap. So by turning on a magnetic field, I can make them run in circles, right? Just like what I showed you in the quantum Hall effect. So they don't conduct anymore. My resistance very quickly go to very large values as I crank up the magnetic field. Okay. What? This is usually 1.5. If I don't mark it, it's 1.5. Sorry. Yeah. Okay. So for this configuration where I do have the kink states, they live inside the gap. But if I turn on a magnetic field, I also get lambda levels inside the junction. And those are the states that I've drawn over here. Right. So now if I change my Fermi level, inside the gap, I have a resistance of h/4e squared. But if I go into the conduction band, each time I cross a set of lambda levels, which has degeneracy of 4, I gain another 4e squared over h in conductance. And then another lambda level, it becomes 12e squared over h. Right? Okay. Same that happens with the valence band. Right? So this is the band structure inside a magnetic field. there's an added benefit when you turn on a magnetic field is that these lambda levels are moving up as you crank up the field. So at some point, they make the gap larger than what you set out to have. And having a larger gap is good. Your quantum wire become more robust, and you will see that also in the data. So this is showing the resistance of one channel as a function of the silicon gate, which I use to sweep the Fermi level. You see two plateaus. Okay. This plateau is roughly h over 4e squared. This one is roughly h over 8e squared. The difference between them is precisely the difference between these two. There's a different device over here. You see more plateaus, h over 12, h over 8, h over 4, and then on the other side, another step. Okay. So these plateaus corresponding to the conduction inside the gapped area, and that is roughly 4e squared over h, or resistance h over 4e squared. So this is the reason that we are calling this quantum valley Hall effect. Remember the 4e squared over h that I wanted to get. If you have good eyes, you probably realize this is not 6.5, but rather 7.5 kilo ohms. And each of these plateaus are modified by that same delta. And that is the contact resistance. I'm doing a 2-point measurement. I always have a contact resistance, which goes on top of all the plateaus. Okay? Yeah. Of those states inside the junction.
So it's like
the normal, correct.
Gap in the bilayer.
No, the bulk is still insulating. These are the states inside the junction.
Classic.
These are your normal vanilla quantum Hall effect. Right. So that's the quantum valley Hall effect. Right? Okay. So this was 6 Tesla. Okay. As we lower the magnetic field back down towards 0, you can see that this plateau first stayed at h over 4a squared, but when I really lowered the field to 2 and 0 Tesla, the resistance actually dropped. Okay? It's not because they became more conductive. They cannot be more conductive than ballistic. Right? The reason is that, remember the parallel conduction that I showed you before in the control situation, right? So that turned on. And the two of them conducting in parallel brings the resistance down a bit. So with that model, we can in fact back out what is the resistance of each channel of just the kink, right? And it turned out to be roughly around 7 kilo ohms at B equals 0. So we're not entirely ballistic yet, but getting there. Hopefully in the next set of samples, we will be entirely ballistic. A few more samples. Roughly corresponds to a mean free path of 3-4 microns. So that's sort of about the state of art in this system. Okay, so when did I start? No, is there a clock in the room? Oh, okay, so I should go very quickly to show you how we partition the current in this system over here, right? Okay, so the underlying mechanism for making a valve, right, has to do with the fact that because I'm creating this system by applying a gate voltage, I can do it in minus plus, which I get this, or I can take the thing and flip it around and do plus minus, and that turns the arrows around, right? Okay. So you can think of as two helicities of the system, right? The electric field going this way versus the electric field going this way, right? Okay. Now watch what happens when you put two of them together. Let's suppose I put them together in the fashion where the valley indices are aligned, right? So my arrows are also aligned. In this case, I expect the state to just propagate through. So that's the on state. But if I put these two guys anti-aligned together in this fashion, now if you're tracking, you will see that states traveling up, the blue guys, need to now switch into the red guys, an intervalley scattering, in order to keep propagating. Right? And if I don't have intervalley scattering, that's not allowed, so that's blocked. Same thing that happens with the states that are traveling down. Okay. So here comes a situation where my current could be valley unpolarized, has both blue and red occupied. Yet I have a blocking effect, a valve effect in both valleys, and therefore you can make a valve out of it. If you work on spintronics, I know some of you do over here, you realize this is different from a spin valve. In order to make a spin valve, you first have to spin polarize your electrons, right? So here I have valley unpolarized electrons, but because of topology, because I locked valley with momentum, I can make a valve even in this case. And that's what we call a topological valley valve, because it uses the topological aspect of the system. So this is a simulation, a wave packet simulation done by my colleague Ivar Martin that compares these two cases. So in the on state, you see the wave packet traveling through, because there's no state here, no state here. In this case, wave packet can't travel through, it's blocked. Instead, you see that there are states here and states here, and you see the splitting action of the wave packet. Right? So at b equals 0, you make a 50-50 beam splitter. Right? But we can actually do better. We can tune the beam splitting if you allow me to put a magnetic field through the sample. And this works roughly based on the Lorentz effect. Remember that these states carry different group velocities, opposite group velocities, which means they also experience the opposite Lorentz force. So that pushes the wave packet, wave function of k and k prime, slightly away from each other. Okay. It turns out that at the charge neutrality point, there is a symmetry that keeps them together all the time. Okay. So that's this case. But if I start tuning the Fermi level away from the charge neutrality point, in one direction, k shifts to the left, k prime to the right. And then if I crank the EF more, I see more of a separation. This now starts to look like the chiral edge states of a quantum Hall system, right? And if I now change the Fermi level to the opposite direction, my k and k prime go to the opposite, and this is the limit of that. So now if I send a current, let's say it's carried by the k electrons, that's the excess current, you can see that in this limit, it could only turn left. It could not turn right because there's no overlap between these wave functions, whereas in this limit, it could only turn right. And as I scan through the Fermi level, I can go from 100% to the left to 100% to the right, passing through the 50-50 point at the charge neutrality point. So that's a chirality-based electron beam splitter. Right? Okay. So that's indeed what we saw. And I'll quickly show you the data. So this is the resistance of one channel, second channel, two channels together. You can see that the resistance hasn't changed. If you put two resistors in series, you double that. But because here the wave function is traveling ballistically through, I haven't changed the resistance at all. It's all around h/4e squared. Right? So that's the on state. In fact, I can make a waveguide that makes a turn. Right? I don't have to make a straight one. I can make a right turn, make a left turn. I get roughly about h/4e squared also. I do it in this valve off state, plus minus, minus plus. I send a current in. I measure the three terminals simultaneously to see which one gets a current. This channel always gets very little current. That is because of a valley blocking effect. The valve is working. But if I look at current received by this terminal and this terminal, you see this X formed by their current. On this side, the current flows all here. On this side, current flows all here. So that's the beam splitting that I mentioned earlier. Okay? Okay. So just a couple more on beam splitters. Right? How beam splitters are good. We know them from Michelson-Mollet experiment. We know their important role in photonics, in creating entanglement. In electrons, it's much harder to do. It turned out that there's only one beam splitter available right now, which is a quantum point contact for chiral edge states of a quantum Hall effect. So we have another beam splitter here that could work on the kink states And what we're doing now is to make it work at b equals 0, and hopefully to do interferometry measurements on these systems. Okay. So I'm going to skip over the theory aspect of it and just directly summarize, and hopefully I've convinced you that we created what I think of as a cool one-dimensional helical system. If someone can grow bilayer graphene on a wafer scale, we can pattern the system on a wafer scale as well. Then you would have a network of these gate-defined channels. Right? So I've showed you a bit how we control the traffic, right, by using these mechanisms here. And I've spoken to a few theorists who are excited about coupling these things to superconductors. Right? So it's a helical, I don't know, where's the Curiel? System over here, right? So we're thinking along these directions and how to use this cross as a quantum point contact to probe the interactions of these 1D systems. So feel free to ask me about it. I'm still here tomorrow. And with that, actually the most important thing. So this is Dr. Jin Li, who is now at a director's postdoc at Los Alamos. He's my hero who did all the experiments that I just talked to you about. Collaborators, theory collaborators, an experimental collaborator from Japan who gave us the HBN crystals. And well, thank you for your attention. And you can't put the Fermi level inside at the charge neutrality point in the gapped region. Right? If I just want to, you will have, as long as you have an inverted bands, you will have these states. But you will also have other trivial states at the Fermi level. And you would measure them together. Right? You're right. If you just wanted to create an inversion, you don't need that. But in order to measure it, you do need that. How what? How important it is?
Yeah, so I see the level is not exactly not only the absolute value, but also.
Yeah, so that part, that's a very good question. So those wiggles actually aren't from the wire themselves. They're from the contact area, which I didn't talk about. You are thinking of these wiggles, right? And also some of the wiggles that I showed earlier. You notice that they are actually overlapping on top of each other. So they came from this axis region that's here and here. And we kept them the same in all three measurements. That's why these wiggles overlap. So we have separate measurement to show that indeed that is the case. Right, right.
So does the intervalley scattering? Why don't we see?
What do I think the intervalley scattering is? So my guess is that we still have occasional electron hole puddles that's also at the Fermi level. And you can swap K to K prime and also swap the valley index of that charge puddle. So higher order process, but it can happen. So if you clean the sample, meaning make the interface clean all the long-range Coulomb fluctuations, I think we will do much better, and that's what we're doing. So open up the gap and clean the interface.
So if you had another cool down, so presumably all three curves are measured in the same cool down, right?
Correct, one after another. We did that in one device. Those patterns will change. It will be a new pattern. So that's also another reason we know. There's also another reason we know. I had another slide that I didn't show. I have 100 backup slides, guys. That's why it took so long to transfer. I don't know, where's that presenting button? Is it here? Right. So you can see this is sort of 3 different devices. You can see that each one had a different top. If you get lucky, it's flat. If you don't get lucky, you got these wiggles. This guy is tilting, and the magenta looks like that. So for the magenta, we actually separately just measure the axis area, and it looks like that. You see this really follows that, right? Right. So we know it's from here and here. And sometimes you can get lucky, and it looks flat. Yeah.
Maybe one more question?
Yeah, so you started by promising conductance without resistance. Now, these silicon mold wires have 6 kilo ohms, and there is no way this is real dissipative resistance, even though this is ballistic conductors, right? So this is source of dissipation.
So this is what I claimed very honestly from the beginning, that my ballistic wires have quantized conductance. They're not superconductors, right? So the dissipation happens at the contacts. The voltage drops at the contacts.
When you enter or exit.
Correct. So you'd hope that you would do information transport and manipulation within this network as much as you can do before you exit at the contact. Within this cross, when I do this current splitting, I know it's ballistic.
Even when it turns, it still is ballistic.
Correct, because I still get H over 4A squared. And when I split, if I measure the 2-terminal resistance from the terminal to all 3 together, it's still H over 4A squared. But you cannot avoid exiting the system, and then therefore you will drop a voltage. Yeah.
So with that, let's hold any other questions. She'll be here tomorrow to give a more detailed seminar on other things. So if you have more questions, please come back.
Thank you.